So I'll start with talking about an introduction to neutrino oscillations, which means long baseline oscillations, and then I will talk about the technology of using liquid-Argon time projection chambers to detect those neutrinos. And then I'll spend the last part of my talk to talk about short baseline neutrino oscillations and the experiments we have recently brought online for that. So I don't think neutrinos need much of an introduction here with you. They are the most abundant species among the most abundant particles in our universe. They span a huge range in neutrino flux and energy. And I think you're aware of all this, but I want to point out the neutrino beams, which is neutrinos from accelerators that are going to be talked about in this talk. They're around GeV energy, so it kind of falls right here, just to give you an idea of where we are on the scale for our experiment. What I like about neutrinos and why I like working on this, one of the reasons is neutrino detectors are usually not a single purpose experiment. You can do a lot of different measurements with them. And that's also true for the detectors I'll show you in this talk. So there's a couple of open questions in neutrino physics, and I know some of you are working on answering some. Neutrinos, are they responsible for matter or antimatter asymmetry, or do they have anything to do with it? Are there more than the 3 known neutrinos? How do neutrinos get their mass? What is their absolute mass? What is the mass ordering? Is unanswered yet. Can we probe other BSM physics with neutrino detectors? And what can we learn about the universe with neutrinos as messengers? And we have a couple of different experimental approaches to look at those, and a very complementary picture, which is a good thing that multiple technologies can try to answer the same question. That's exactly what you want. So neutrino oscillations target some of those, as well as what many of you are working on. Neutrinos have a beta decay experiments, and then there's actual particle physics and cosmology. That's quite a lot. So this talk really will focus on neutrino oscillation experiments and the physics in terms of neutrino open questions that we can do with those. So as an introduction, everything starts with the concept of neutrino oscillations, which means that neutrinos are produced and detected as neutrino flavor eigenstates. We have the electron, muon, and tau neutrino. But those are not the actual fundamental mass eigenstates of these particles. For neutrinos, they differ in the standard model. And so we have neutrino mass eigenstates, which we call 1, 2, and 3. And they relate to their flavor eigenstates through this PMNS matrix, and it transforms the combination of a mass eigenstate into a flavor eigenstate. The PMNS matrix is the analog to quark mixing in that sector, and so the analog to the CKM matrix. And you see here a picture of both of these in the bottom. The elements here that you see in the CKM is the kind of size of the boxes resembles the size of the matrix element. So the CKM matrix is rather diagonal with the strongest elements here. The PMNS matrix looks very different. And right now we don't really know why that is, if they should even be related and have any symmetry between them, and if that maybe has to do with the very different mass scales that these work on. But it's something of interest to answer. If you factorize this mixing matrix here, you can break it up. This is a choice in these 3 different terms. And each of these terms has a mixing angle that is a free parameter that we try to measure in oscillation experiments. These are named 1, 2, 1, 3, and 2, 3, based on which neutrino mass eigenstates mix with each other. And then there's the CP violating phase delta CP, and some non-measurable Majorana phases that are not shown here. The nice thing is that basically for each of these angles and these brackets of this mixing matrix, we have different experimental approaches, and 2 in each case. So this mixing angle 2, 3 is dominant, this term, for atmospheric neutrino measurements as well as accelerator measurements. So you have 2 handles on measuring these. This middle term here is accessible for accelerator and reactor experiments. And then this one here, this red one, is for solar and reactor experiments. And when you do a neutrino oscillation measurement, as you all know, you don't really observe the neutrino. So what you really observe is the neutrino interacting with particles. And then what we measure is basically a neutrino count, and that relates to the probability of a neutrino that was sent out from a source still appears at the detection, still arrives, or if it has disappeared and transitioned into another neutrino flavor, or if a neutrino flavor that was not part of what the source originally sent has appeared in the detector. So we call this appearance and disappearance measurements, and our counting of neutrino numbers relate to these what we call survival probability, which tells you either a probability for a different flavor to appear or for a existing flavor to disappear. And this relates to these matrix that we've seen before. And the parameters that are important in this mixing game are this one here, the squared mass difference. So the mass difference between the neutrino mass eigenstates, the baseline of your experiment of which you observe the oscillation, and E, the energy of the neutrino. So that gives you a couple of more free parameters. In addition to the 3 mixing angles you've seen here, the CP violating phase, you have squared mass differences 3,1 and 2,1. And then another unknown is actually what the sign of delta M squared 3,1 is, because what you can see here is we have 3 neutrinos. We have relatively well measured these mass differences between them. One of them is small, one of them is big, but we don't know if the small one mass difference is the lighter 2 neutrinos and the big one is to the heavier one, or if it's the other way around, if the neutrino 3, where we have the big mass difference, is the lightest one and the other 2 are heavier. So it's another question to resolve for neutrinos. So here's kind of an evolution of how well we know all these parameters that play a role in long baseline oscillations as a function of time. And you see, we started out from not knowing much about it, like 20-ish years ago, to actually knowing a lot about these parameters. There is one that is known to 5% here, squared mass difference known to now 1%, although this is the one where we still don't know if it's what the order, the mass ordering of the neutrinos is. And then the one that is the least well known now is the CP violating phase, where we're still on. And that's what the current and next generation of neutrino experiments really is trying to get at. So if you do an accelerator neutrino oscillation experiment, what it typically involves on a very basic scale is you have a beam of mu neutrinos or anti-mu neutrinos. You will always have a continuation of some other flavors, but it's primarily one flavor of neutrino. And you send it over a certain distance, which is typically many kilometers, even many 100 kilometers. And then you measure the disappearance. Most of those beams contain mu or mu bar. So you can measure the disappearance of these neutrinos. And at the same time, you can measure the appearance of a different flavor of neutrinos, mu E or mu E bar, at your detector location. And typically for these experiments, you have a near detector, so you can strain your originating flux and the uncertainties of that. So it's a two detector concept in one neutrino beam. And there's 2 of those that are going on right now. One is in Japan, that's the T2K experiment. The other one is in the US with a beam from Fermilab, and that's the NOVA experiment, which is located in Minnesota. And they are a little bit complementary in what they do. They have different energies. One is lower, one is higher. They have different baselines. Lower energy also goes with the shorter baseline. 295 kilometers for T2K, 810 for the NOVA experiment. Different far detector technologies and masses, but they're basically kind of trying to do the same thing. It is really important to have these 2 different approaches and slightly different detectors, both in technology, but also in baseline and energy, because there's some ambiguities, which I'll walk you through in the next few slides when you try to do this measurement. So input from multiple experiments at different baselines and energies is crucial, as you'll see. The experiments also try to measure several channels simultaneously to try to get a better handle of their uncertainties. And then they also use external measurements, often from reactors, to constrain some of the oscillation parameters that they're less sensitive to themselves for their fit in the end, fit for the end result. So this is kind of a concept of one of these measurements broken down from simple to more complex. Very simplified, an oscillation analysis is a counting experiment. You send out a beam, you count how much neutrinos versus anti-neutrinos you measure in your far detector. And if you have vacuum and no CP violation, you expect that you have the same probability for neutrino and anti-neutrino appearance or disappearance in the case of neutrino oscillation. So in this kind of measuring the asymmetry, this line here in the center is symmetric, which means your measurement point will be somewhere on this line, if this is your simplified universe. And the distance here depends on one of the mixing angles. Now you add CP violation, which means that neutrinos and antineutrinos will not behave the same way. So the result you expect will no longer be located on the line. It may only be located on the line if you have no CP violation, which means delta 0 or delta pi. This is the CP violating phase. And then otherwise it will be located on this ellipse here with values for maximum CP violation, pi half or 3 pi half, which these are the extremes here. So your measurement will be located somewhere here. Then you add matter effects, because neutrinos traveling through matter from the beam through the hundreds of kilometers to your detector will be affected differently by the matter in the Earth than antineutrinos traveling through matter, both traveling through matter, but neutrinos and antineutrinos, different interactions with matter. So what does that do is it separates the two ellipses depending on what mass ordering we're in, depending on which of the two neutrinos are closer together versus further apart in mass. That's the graph we have seen earlier on. And so it will create two different solutions, assuming inverted, which means the nu3 is the lightest, or normal ordering, which means the nu3 is the heaviest. And your measurement will be located either on this ellipse or on this ellipse, depending on if you live in normal universe or inverted universe, which we don't know yet. And then what I want to point out here is these affect the impact of mass ordering on your measurement is different depending on how long the baseline is of your experiment. NOVA has a longer baseline of 800 kilometers, so the ellipses separate much more than for the T2K experiment, where they have a shorter baseline, so they only separate a little bit. So you have different degeneracies in two experiments when you do that measurement. And these are kind of the current results, which are also very interesting. So for CP violation, basically, these are the graphs from the NOVA experiment, and this is from the T2K experiment. You see here, these are their expected ellipses in the phase space where they live. And then this would be the line going through, kind of. And in the middle is no asymmetry, and this is what NOVA observes, no asymmetry. T2K, the opposite, when you look at their different ellipses, you see that the measurement is actually at one of the extreme ends of their different predictions. So they see maximal CP violation. So that's unknown. There's tension between the measurements, and it is not resolved. They have done a global fit, a joint fit of their results, which kind of splits the difference a little bit, but doesn't really give us a lot more answers beyond of what we learned from these plots. In terms of mass ordering, there's a slight preference for both NOVA and T2K for normal ordering, which would here be the blue ellipse, and then from T2K, you can see the one on this side. And so that's where we're at. That's where we're living with the current generation of accelerating neutrino experiments. Yeah.
I'm so sorry. Can you go over those two? Like I can see, can you just go over these? I'm so sorry. Like the cross in the like the banana area for the, yes, I'm so sorry.
Yes. Okay, so the ellipsis is the prediction, the same ones we have seen before. The cross is the measurements, and then the area around it is just the significance range that they color shaded in this. And then the line depends to 1 sigma around the measurement.
Thank you.
Sorry, yeah, no, that's very, very valid question. Good. And I want to make a note that the accelerator experiments are not alone in trying to resolve this. I'm not going to talk about it in this talk, but there is measurements that you can use with atmospheric neutrinos that provide a complementary approach to measure these parameters. They're at the range where they're competitive for mass splitting and large mixing angle results with the latest long baseline accelerator measurements that you see here. And then there will be a future experiment, Juno, which I don't have time to talk about either, but that has very promising sensitivity to measure the mass ordering specifically. If you want to resolve the CP violation question, really, you want to go to the next generation of long baseline experiments. And that is Hyper-K and DUNE. So you can think of these a little bit as T2K being the evolution into Hyper-K, and then NOVA kind of going into DUNE. T2K will be located in Japan. DUNE will be located in the US with a beam from Fermilab. Hyper-K experiment will be an upgraded beam over the same baseline as T2K has, and will be a huge water Cherenkov detector and an upgraded near detector complex. So everything new, the huge detector with a huge volume of water as a target will give you a great amount of statistics for that measurement to get more sensitivity. And then on the other hand, DUNE will be a new beam from Fermilab. The far detector will be located in South Dakota with a baseline that is even slightly longer than the NOVA experiment. It will be in phase 2, 2 liquid-Argon time projection chambers, more planned than for phase 2 of the experiment. So it's phase 1 and then phase 2 more. And then it will also have a brand new near detector complex that is multi-purpose and will help with the systematics measurements of the experiment. There is complementarity between Hyper-K and DUNE, and I think that's really important for our program to understand these open questions. Again, Hyper-K has a shorter baseline, or will be less impacted by the beam going through matter than DUNE, the long baseline, which has a large matter effect. large matter effect and typically increases your sensitivity to mass ordering. Hyper K has an off-axis detector with a narrow beam. DUNE is an on-axis detector. Their beam energy spectrum is more broad than the Hyper K one. In this lower energy range where Hyper K is, the dominant scattering interaction process is charged current quasi-elastic scattering. While in DUNE, if you have a broader energy range and you have higher statistics over the full oscillation region, but you will have different scattering processes involved, including resonant and deep inelastic scattering. And then, as I said, very large water Cherenkov detector for Hyper K, huge statistics. DUNE will be a liquid-Argon TPC, really nice resolution. And I think you have had a talk about DUNE very recently. So I think this is where I want to abandon DUNE for this talk and talk a little bit more about the technology of the liquid-Argon TPC. Unless there's questions on long baseline.
One question is, I don't know if this is up to date, but I think I've seen in the past plots indicating that Hyper K and DUNE would have like fairly similar mass ordering sensitivities. Is that, first of all, is that correct? And second of all, how does that work if the matter effect is a lot smaller in Hyper K? No, it's not correct.
No, they shouldn't have the same sensitivity.
Okay,
What
okay.
you can do though in Hyper K, you can add atmospheric neutrinos.
Okay.
And do a measurement with atmospheric neutrinos in the same detector, and that then will help you again.
I see.
But by itself, this is truly different baselines. So this is very simplified how a LArTPC works. You have a large volume that is filled with liquid argon, which acts as the target for neutrino as well as the detection medium. We have a cathode on one side and the anode on the other side. 500 volts per centimeters, roughly the electric field we work with. The neutrino comes in undetected. If it interacts in the detector and produces secondary particles, which are these kind of red lines here, those secondary particles, if they're charged, they ionize the argon. So you will have a couple of ionization electrons, which are these blue dots here. And then because of the strong electric field, those will drift towards your anode. And on the anode, they will be detected by a grid structure of wires. Typically, we use 3 different planes, and their wire directions are 60 degrees with respect to each other. And then from the intersections of the wires, you kind of get some spatial resolution. Behind this grid of wires, we also have PMTs, and they catch the light that is produced in the scintillation at the very early interaction of the neutrino. And then this is kind of what the signal looks like. This is a bird's eye kind of view on the TPC. So you can see here at these dots, these are the wires, the first, second, and third layer. And there's a little biasing field around them so that the electrons will actually drift towards them, but then around the first 2, and then they will be collected on this last wire plane, which means that you have bipolar pulses on the first 2 planes and then a unipolar pulse on the last plane. That's how you read out your signal. This is how it looks like in the end, such an interaction. So what you get is bubble chamber-like images, but you have 3D resolution to those, because the time of arrival will kind of give you the depth. And then you can do calorimetry, and calorimetric information, we'll get to that later, is encoded in the color in these pictures. So these are the 3 wire plane views: induction plane 1, induction plane 2, and collection plane. Collection plane is typically the cleanest, just because the noise subtraction and the extraction of unipolar pulses is easier for us to do. And this is, so then this direction here is time. Basically, it's the same, the depth from the anode to the cathode. And then this is just basically the wire number that you go through. And so this is the same neutrino interaction, but the 3 different views. The neutrino comes in undetected kind of from here. Here's your interaction point. And then you get a couple of secondary particles that go out from here. Tracks, we categorize them in tracks and showers, electromagnetic activity here. And then there's a couple of things that just randomly go through, and these are cosmics because the detector is located on the surface and you have a relatively high rate, so there's multiple cosmics typically overlaying a neutrino event in your image. Here I want to show you how this in reality looks like on a detector that we just recently built, short baseline and near detector. So this is a schematic of the detector. It's actually 2 TPCs that are in one cryostat. The cathode is in the middle and they share it. And then we have 2 anodes on the other sides. The 2 halves look identical. Here's a picture looking into the east, and here's a picture looking into the west. So the same thing with the cathode on this side. Picture of the cathode is here. It operates at 100 kilovolts. And so the maximum drift time from electrons all the way from the cathode to the anode for the 2 meters that our detector is wide is 1.28 milliseconds. And so there's some reflective foils in there in these what we call windows that help as an approach to reflect some of the scintillation light that gets emitted towards the cathode to regain it back by reflecting it back to the direction where our photon detectors are. Then you have the anodes. So you see a picture here of the anode plane of the 3 wires. The wires you can't see, but kind of you see the reflection off of the wires in this photos here. They have 3 millimeter space. There's a total of 11,000 in the detector. We have 4 kind of individual frames that hold wires, and 2 of them were produced here at Wright Lab. And I was here, my only visit to Yale before in 2018 to see the production. And at the same time, also the field cage, which you see here. This is a structure of kind of loops at the same electric field that goes all the way from the cathode to the anode to step down the electric field in equidistant steps. They were also produced here at Wright Lab. 16 of those are surrounded. Then we have cold electronics. They're submerged in the argon. They pre-amplify and digitize the TPCOR signals in the cold before the signal comes out through our pixels. And then we have a photon detection system. You see a photo here, photograph here. That's different than every of the detectors that we have been doing. But here we have traditional PNTs. And then we have these little light traps. They're called X-ray-pukas. They are read out with siphons. And then this is one example, but all of these detectors kind of have similar, they look similar. So I want to go through some of the strengths of this technology and why it's so useful for this type of neutrino oscillation measurements. One of them is low particle thresholds, and this low is relative. I know that some of you are working on very different scales here, but for a detector that does this type of physics with GeV beam neutrinos, these are very low thresholds and a very nice imaging. So basically, you try to resolve the shortest particles possible with often our protons in our case, and the protons are important because they are part of the neutrino interaction. They're not only in the long muon produced, which is easy to detect, but the proton has part of the energy and part of the information on what happened in the interaction. And the protons are short. You kind of see in this graph the proton range in kind of centimeters versus the kinetic energy, right? And if you go just based on basically wire spacing, you end up somewhere here, and but then an effective threshold is in reconstruction somewhere here. So you're in the few tens, 20, 30-ish MeV kinetic energy threshold for protons, which is really good. The way this threshold comes into play is you see how our wires are spaced. When you want to reconstruct a track with a direction, if you have only one hit, because proton is so short, that's basically impossible. If you have 2, that is better, and depending on what direction your particle has with respect to your wires, this corresponds to a lower or a little higher kinetic energy. And then if you have a lot of events and you need to run automatic reconstruction, it's a little bit more safe to require 3 hits to really make a track. And so that gives you a threshold of around a centimeter in the case of MicroBooNE. ArgonUge, I had not so many events, so they can scan a lot of their events. And then they really could pick some protons and identify them where there were only 2 hits. And that's one of them here. And it's kind of half a centimeter length, 22 MeV was assigned to it as kinetic energy. So it's kind of one of the really lowest that has been seen in one of those detectors. Here you see a picture from MicroBooNE. This is a 2 centimeter scale. So this is a little bit longer, but you can still see this should be able, and we are able to reconstruct it with the automatic reconstruction chain. But then if you look over, this is how big an entire readout is. It is a really, really tiny particle among everything else. So it's not too easy to find, but it is possible. Another strength for LArTPCs is that we can do calorimetry with them and for particle ID. And so the calorimetry is done by measuring the deposited charge, which in a bubble chamber image we don't have, but in a LArTPC image we have that. And the deposited charge is decoded in all of these event displays you typically see in the color. So blue means that there's no charge deposited, or basically corresponds to our noise level. And then the more red it gets, the more charge was deposited. And let's see this as an example here. This is a muon that comes in. It's kind of green. Then it stops. So it's the bragg peak where it deposits kind of all of its energy, and it makes a super short little electron that curves up from here. If you do that for a lot of tracks, you can measure the energy loss as a function, the EDX, as a function of the residual range. This plot here is from the proto-DUNE detector. And it shows you here the different populations of the muons. They're down here, minimum ionizing particle. And then if you have higher ionizing particles like a proton, they have a different population in the plot like here. And then other particles like kaons, pions, and so will be in between. But this is a plot actually reproduced from data, so that's really nice. So this is how you do it. And this helps you with identifying the particles in your interaction and doing the physics. And another strength that is really key for these measurements is to separate electrons from photons in this technology. Because what you're after if you do an oscillation measurement is you need to find out if you have a muon neutrino or electron neutrino, where you need the flavor. Muon is easy, it's a long track. Electron makes an electromagnetic shower, and so does a single photon. And there are many standard model interaction processes that make single or two photons where you might have trouble to identify the second one or so. And they're a huge background for all these electron neutrino appearance measurements. And a lot of the previous experiments at which data we're looking at right now, I'll get to that later, they have this struggle that they cannot distinguish between a shower induced by a photon and an electron. But here's what we do. You have two handles in a LArTPC. First of all, if you can find a neutrino vertex, and there is a gap between the shower start and the vertex, then this was the gamma, because that is invisible in the neutrino TPC. So you had a photon that then started to shower at a certain distance. If this was an electron neutrino interacting, the shower from the electron would start right at the vertex. So you have that. Now here we come back to the low threshold that you need for finding this proton. Because if you want to find the neutrino vertex and there's no muon involved, for example, because an electron interacted, you need to find the neutrino vertex by finding that short little proton stuff to use this technology, separate electron from proton. Then you have another handle, and that's the energy loss. Because if the electron initiates the shower, it's a minimum ionizing particle, and you can measure that energy loss of about 2 MeV per centimeter if you look at the very, very beginning of the shower, just the first couple of millimeters. And that's about 2, and you see that it's the green population, electron, neutrinos interacting, charged particle. And then if it's a shower, if it's a photon creating a shower, it will start to shower with pair production, E plus, E minus. So you will measure at the very beginning of the shower the energy deposition of 2 minimum ionizing particles, which is 4. And you see that the blue population here is mostly at the 4. And so you have these two handles. Yeah.
For that one, would it always to have the two, in that case, it's like the two gammas? That would be, is it always from a pi 0?
Typically, yes. It doesn't
Okay.
have to be, you can have a coincidence of
Okay.
or a more rare process that has a pi 0
Okay,
that then gets that. But yeah, this is the most dominant background.
thank you.
Right, I have name dropped a lot of LArTPC experiment names already, and while I was preparing this talk, I thought I should try to make sense of this. So I tried to make this graph, which kind of sorts them all in the time of when they started operating and the mass that they have. And this is on block scale. So you can see it started out with a tiny 50-liter test experiment. It was called ICARUS and operated at CERN. And now we're on track to build the DUNE car detector modules, where we go into the tens of kiloton range of masses. So all these last decades, we kind of have been trying to build up to this with experiments that were both in neutrino beams, that's blue dots, and then I overlaid these red squares when they were actually operating in a test beam, which still gave us a lot of experience in building and operating the technology and refining, for example, the reconstruction and such for these experiments. So you can see that this is expensive, so we are fan of reusing our cryostats. So ICARUS was moved to ICARUS at a large scale at Gran Sasso, then we moved it to Fermilab with basically the same detector, different cryostat as well. Then we had Argonute as a test experiment here in the US, later reused as LARIAT, also at Fermilab. And then we had proto-units run again in the same cryostat and on and on. And this year, 2024, was actually a really good year for us because we brought online quite a couple of experiments. There was the short baseline neutrino experiment, which started operating this year, also the 2x2 demonstrator, which is a prototype for DUNE operating at Fermilab, and then the 2 proto-dunes, again, in the test beam at CERN. So it's quite a lot of success for us. I want to point out something else on this plot. Not everything is just R&D for DUNE, but there's kind of a sweet spot here in this region where you seem to have a really good mass. And it's not just because this is a still convenient size to build. It's kind of like house size you experiment at that point. But it's also because you can do very interesting physics for medium-sized experiments at operating at short baselines and not at just hundreds of kilometers. And that's what I want to spend the rest of my time on. Okay, short baseline oscillations. So the story of short baseline oscillations starts with anomalies that were observed in the long baseline oscillations, or basically in that pattern that people knew, not really in long baseline experiments. But they were experiments operating at baselines and energies where no oscillation was expected based on all the mixing parameters we know. However, they saw things that didn't fit with this pattern, and that's threefold. There's reactor experiments. They operate at relatively short baselines, but also low energies. And reactors produce antineutrinos, anti-electron-neutrinos, and at all the detectors around it, there was fewer of those detected than predicted from the source. So there's a deficit here. The other channel that we have is there are source calibration experiments for solar experiments. That are the gallium experiments, as they're called. And you see those at this spot here. And they measure rates expected versus what they have measured. And you can see they have electron neutrino sources, but then in their detectors, they measure less than expected from the source. So there's another deficit in this channel here. And then if we go to experiments that measure the appearance of neutrinos, electron neutrinos in a beam of muon neutrinos, that is LSND and MicroBooNE, they expected close to a very small contamination of electron neutrinos, so close to zero, but then they do see the appearance of electron neutrinos. So they see signal where nothing was supposed to be, so all of these. And then it was believed that all these observations can possibly be put under the same hood by adding sterile neutrinos, one or more, that is a lot heavier, around 1 electron volt per mass difference to the existing neutrinos we know. And if we add this into the mix, this one or more sterile neutrinos, it could possibly explain all this oscillatory behavior that was not on the 3 neutrino oscillation plan. But one has to remark that there's also channels and experiments where if there was a sterile neutrino, we would expect to see muon neutrino disappearance, for example, from a bunch of experiments like atmospheric neutrino experiments, and they have not seen that. So it's not a clear story at this point. So based on these initial anomalies, there was a lot of work in the last years to follow up on that. And then starting out with one slide on the reactors. So the reactors have now established that there is a 6% rate deficit from the anti-electron neutrinos that are sent out by the reactors. But new data suggests that this could be due to the modeling of the underlying uranium spectrum that goes into all of those measurements. And then they do spectral measurements. This is kind of more powerful to do than if you just measure the rate deficit. If you look at the energy spectrum, if you look at the spectrum at different baselines, which is always a good handle for oscillation experiments, and then in particular the ratios of that. And if you do all that, you basically range at, you do not observe a deficit of, you do not observe a lack of the neutrinos, and you can come up with a limit that cuts significantly in this previously favored parameter space of an additional force neutrino. And this kind of weakens the sterile neutrino hypothesis quite a little bit. Then if we go to the gallium anomaly, in addition to the first two experiments, SAGE and GALEX, there was the BEST experiment, which was designed to follow up on this deficit, and BEST kind of confirms they also see this deficit in this type of measurement of around 20%, which brings this deficit to a significance of 5 to 6 sigma, so that's quite a lot. If you go into this sensitivity plot, very similar plot as before, but kind of different colors for the lines. But the one from the reactor rate deficit would be the green area ish, and then this gray area is if you do the spectral analyses, all that's included, and it kind of is in contrast, in tension with this blue area, which would be what is the favored parameter space for sterile neutrino, if you interpret this as a sterile neutrino result. However, so in addition to this tension between the gallium anomaly and the experiments like solar and reactor, in this scenario, it's also important to mention that they did 2 measurements, an inner and an outer, which means they have 2 different oscillation distances to test, and they didn't see a significant difference. So at least at these baselines that are accessible to the BEST experiment, there's no oscillatory behavior that would create a difference between 2 different baselines. Okay, and then we get to the accelerator low energy axis. This was the opposite, where they have too many neutrinos rather than too little. And this is a measurement from LSMD as a function of L over E, and then it's the minimum experiment as a function of energy. So here you see the backgrounds is just the green and the red. And so what they measured is this, the black data points, and the blue that they have overlaid is a possible force neutrino interplaying with all that. And that would describe their data reasonably well. And in the MicroBooNE case, you have this plot where you have all the backgrounds stacked in color, and then the data points are black here, and you see that they measure an excess at low energies as well over the expected background. What I want to point out, especially for MicroBooNE, is that this is a detector that doesn't have the capability to distinguish electrons from photons, really, because an electromagnetic shower event kind of looks like this, both if it's from an electron and from a photon. And then especially if you have two photons from like a pi zero, which is all this red background that you have here in your measurement, then it's really hard if you miss the second photon or if it overlays the first one very much to distinguish that. So this is the specific reason why there was a follow-up experiment to MicroBooNE, which is called MicroBooNE, which is a liquid-Argon TPC, so designed to resolve this degeneracy between electrons and photons. So for MicroBooNE coming in, the idea really was that you could probe this anomaly and define what nature it is. Is it electron-like or is it photon-like? It is operating in the same beam at MicroBooNE, same baseline, but different technology. So really you have a very good comparison of those two. And here you see pictures of the events one by one. So this is the MicroBooNE event of a gamma that is maybe electron-induced. And then in our case here for LArTPC, this is an electron shower with a proton at the vertex. This is a gamma. Here's the interaction point with the proton. This is the gap. Here's your photon shower. And then here is a pi zero background where you have two showers, and you can clearly distinguish that there's two showers, so you can be subtracting those. And so you can do the particle ID and the polarimetry, and you have the resolution to do the separation. And then MicroBooNE set out to kind of redo this measurement and kind of redo this distribution from MicroBooNE to see if there is an excess and if it's electron or photon-like. So this is results from MicroBooNE. MicroBooNE ran for 5 years in the booster neutrino beam from 2015 to 2021. And it didn't see an excess. It looked in different channels. Here you see one electron, any number of protons, one electron, 0 proton. This is a distribution. And then you can see here is the electron neutrinos. The blue, again, would be the background with photons, and you see how small it is compared to what MicroBooNE was doing before. And there is no excess. This is very much in line with the standard expectation, and same in other channels. And all this, in total, all the channels that were looked at over 5 years, the results are that these are inconsistent with an electron-like excess at 99%. So what is going on? At the same time, MicroBooNE, of course, also looked at single photon channel to see if the axis was photon-like versus electron-like. But there is no axis in the photon channel either. I don't have the plus here. But the results disfavor a single gamma as the sole explanation of the MicroBooNE axis at 95%. So this really weakens the idea of stereoneutrinos with an axis not even being here. And then to go beyond that, MicroBooNE is trying to place limits on the stereoneutrino parameter space. So you here see the mass difference that you would have for the stereoneutrino and the mixing angle for this third stereoneutrino. This is all in the scenario of one additional stereoneutrino. There could be others. But this kind of bluish landscape is where if LSMD's excess was interpreted as a stereoneutrino, where in the parameter space it would be favored to be. And then MicroBooNE is doing these limits here in the appearance case of alpha neutrinos, and then also in the electron neutrino disappearance. And it's cutting a little bit into this region where the gallium detectors here would have their favorite parameter space with this red line. So the struggle, if you have MicroBooNE and one detector and a beam that has is a mirror neutrino beam and has a contamination of electron neutrinos in it, you have a degeneracy with two competing effects. You can have the electron neutrinos appear because mirror neutrinos from the beam oscillate into electron neutrinos, but also the intrinsic electron neutrino component of the beam can disappear into another flavor, and then you subtract electron neutrinos. So these competing effects at some point in the parameter space kind of cancel each other out, and you see nothing. But you can't really tell if you actually have a lot of oscillation going on and you just don't see it because it cancels out, or if there is no oscillation. You can't tell it apart. So the next step MicroBooNE is going, it's doing an analysis with one detector but two beams, because MicroBooNE is sitting in the BNB baseline on axis, so this is the BNB MicroBooNE detector, but there's a NUMI beam, which is our higher energy neutrino beam that goes to Minnesota, and MicroBooNE is sitting off axis in this beam. So it's not getting the center of the beam, but it's getting off axis beam. And this off axis beam in particular has a very different composition of muon neutrino versus electron neutrino than the booster neutrino beam. And that helps break this degeneracy. And so this is the next measurement that MicroBooNE is working on to make these limits here stronger in parameter space. Okay, beyond MicroBooNE, we're already on to the next thing. We're doing short baseline neutrino program. We built a near detector, and we built a far detector around MicroBooNE. So basically SBND here. ICARUS is the name of the far detectors here. And you can see here, why we do that in terms of event rates. If the MicroBooNE is like 1, then SBND gets 20 more times as many events as MicroBooNE, and ICARUS more than 3 times because it's much larger, even though it's further away. And then they have the same nuclear target, all 3, the same detector technology, and being in the same neutrino beam, this really helps to reduce the systematic uncertainties for these measurements. And that's what we're doing. However, I want to talk about something else, because we have seen now a lot of recent measurements that weaken the idea that this axis is from stereo neutrinos. However, the anomalies have not gone away. The gallium anomaly is still there, the NSND anomaly is still there, and the mini-BooNE anomaly is still there. And people are still looking for explanations of what could it be if it's not stereo neutrino. So there's a lot of potential for BSM, beyond standard model, particle production as byproduct of the booster neutrino beam. And that's a big focus of the SBN program as well to do that. So at Fermilab, the way you produce neutrinos, or also elsewhere, basically you accelerate protons. In our case, that's the booster that makes HEV protons. You hit them on the target, produce kaons, pions. The pions are the dominant parent particle for neutrinos. But in these decays of the parent particles, you could produce BSM particles that also make it to the detector and decay or scatter there, and then you have a chance to detect them. One really good tool that we have to do that is the timing of particles, because the BNB or any neutrino beam is a pulsed beam. It's not continuous, so it comes in these blue little what we call bunch structure that are very short, and if you add particles into that, there are 2 nanosecond buckets separated by 8 nanosecond kind of gap. So this blue is a zoom in. This is the neutrinos from the BNB. Now, if you add a long-lived heavier particle into that mix, it will take longer for those particles from the production to travel to your detector. So you can possibly, depending on how long exactly it takes them to get there, you can possibly detect them in this beam off phases when your beam is kind of down and waiting for the next bunch. And that's your most sensitive handle to measure these BSM particles if they're in the right mass and lifetime range. Of course, you need really good timing resolution for that, and MicroBooNE has kind of shown in the paper that this is possible, and they have come out with a couple of searches. So here, just to show an idea of a couple of models that are around that can produce, they can explain one or more of these anomalies or other interesting things. They typically involve producing new particles and then eventually a decay into what makes an electromagnetic shower, which would be the signal that we're waiting for. So this is the signatures they would make in our detector. The blues are the showers, the red are tracks, protons, muons, which are all really sensitive to, or even low energy detection, little blips. And we have implemented a variety of models into our simulation chain. And so we have simulated images of how this should look like for us. And we're developing analyses on quite some of them. There is results already out there from MicroBooNE on a lot of them, but I wanted to pick a different one. I wanted to pick this search from ICARUS because it is the first physics result that came out of ICARUS, and it was just uploaded to the archive on Friday last week, so it's brand new. And they were searching for a dimuon excess, basically, in the dimuon channel, and they were using this NUMI beam off axis. So we have seen this before, right? NUMI produces their neutrinos and a target and sends them to Minnesota, which goes this way, but then ICARUS is kind of your off-axis, and you could imagine particles, for example, here, hidden sector scalar, this Higgs portal or heavy axion model that are produced, and then they kind of decay in 2 leptons in the detector, and this The search was searching for 2 muons, and then in calculating basically the invariant mass. So this is the plot from after the box opening. In blue and in green, you have kind of the 2 different models of kind of how an excess would have looked like. The search didn't find anything, didn't turn up with an excess. So was placing limits. We should see in some tiny space of parameter space is already competitive or even better compared to what other experiments have done. And this is only the initial data set of ICARUS. And ICARUS is a lower statistics experiments because it's so far away. So you can kind of extrapolate what you can do when you get to SBND with the huge statistics that SBND will be getting. And then some bread and butter physics that the experiments also do is to study cross sections, because as you know, neutrino you only measure once it has interacted. And if you want to conclude to neutrino kinematics like the neutrino energy, which you need for oscillation experiments, that all depends on the mechanics that go on in the interaction process. And that is relatively straightforward with historic experiments where the target material was hydrogen, for example, or helium, which is a very small nucleus. But now our experiments are argon, which have 40 nuclei. There's a lot going on in such a nucleus, and then there's effects of these nuclei interacting with each other, kind of even hiding what particles come out in the end, so you don't know what's the initial interaction like. That's what these particles do as well. MicroBooNE has brought out a ton of results, and I recommend to look at April's talk from Neutrino, where she gave kind of a nice overview of where MicroBooNE is with all that. But just to pick out some highlights, so this is looking for transverse missing momentum, and you can see the dashed lines for models that have no final state interactions, and the solid lines for models that have final state interactions of the nuclei before the particles go out. And so you can see clear difference, clear confirmations that these final state interactions matter. You have here some other channels that are sensitive to different generators that implement different models in their scattering description. And you can see how they can give you a hint of what really is the right theory to use. But we're really at the beginning. There's a lot that from these measurements that needs to be fed into theory and generators. And this is a great opportunity for SBND because MicroBooNE brings all these measurements out with their 5-year data set. SBND will get as much statistics as MicroBooNE in 5 years in only 2 months. So we're already preparing for measurements that we can do very early on that will be very competitive, just because of the amount of statistics. And it is relevant for DUNE because even though the booster is lower energy as the DUNE beam will be like, this is a lot. We have a lot of statistics in the second DUNE oscillation maximum, and even a little bit in the first. I mean, this plot gives you some idea of the overlap in phase space when we do this interaction measurements. Okay. And then last 2 minutes of my talk, I want to give a little bit of status update of SBND because it's the latest detector that came online just this summer. It was an interesting journey, a long journey, but in the end, very successful this year. So the production of the subsystems internationally started already in 2014, and I told you that part of it was done here at Yale, but also in the UK, Switzerland, Brazil, and so on. They have produced systems for our detector. We assembled it in Fermilab through the pandemic, which was quite a challenge. And it finished in fall 2022. This is a picture of how it looks like. Someone was actually sticking that iPhone through one of the slots in the briefcase. And this is how this picture was done. There is no opening to otherwise take a picture from the inside. And then we had to move it across site at Fermilab, which was an endeavor in and of itself, because this is very sensitive. It is really heavy. It was very top heavy. And we planned this for months, and we did test drives and concrete blocks on tracks. And it was quite interesting. There's a nice YouTube video if you want to watch it, like a compilation of how this all went. And then the next big thing we had to plan was to rig it into the cryostat. The cryostat was built in the location of the beam at the same time as the detector. And then the detector set, after we brought it on that loading dock, had to be rigged inside here with a very high rate, obviously. And then it was ready for cool down this year in January. And we did that, and I have a nice, cute little video of how you see the detector fill. This is the liquid level here. It kind of rises up. This is the detector. This is the cryostat wall. Here is our high voltage tree. So how we bring the high voltage to the cathode, which is here in the middle. And exactly, there's submerged now. Okay. The color of this picture also, if you have noticed, it starts out yellow with the LEDs that light up the inside, but then as the LEDs get cold, they change color to green. just kind of fun to see in the transition. So the cryo system is quite elaborate. This is Supraja Balasubramanian. She is a Yale graduate, and she worked with me, and one of the systems she worked on was the purity monitor for our detector. And the purity that we have achieved is really good. The design requirement was a 3 millisecond lifetime, and we have not been able to measure how good we are exactly, but we are definitely much better than 10 millisecond lifetime. So from that perspective, it's a success. Then the video again. Okay. Then we commissioned, so we pulled the detector down, we did some more test measurements, and then we ultimately filled over a period of a month, bringing all the argon. And then we checked our noise levels to the time of the TPC. And the noise levels are also excellent. The noise level changes with a function of wire length. Shorter wires pick up less noise than longer wires, and you see all of them. This line here is for the collection plane wires. They go top to bottom, so they're all the same length. And what you can see here in this graph is around, the RMS is around 2 ADC. And this is really, really close to the intrinsic limit that you can have for a 4-meter wire. So that is better than any of the other LArTPCs that we have built so far. From the noise level, I mean, it's really beautiful. Then we commissioned the beam. And so the beam is being seen by both the light system, this is the PMTs. So the beam arrives at a certain time, it has a 1.6 microsecond window, and you see the PMTs measuring background and then beam on, and the same in the CRT system. So our cosmic tagger also sees that same beam peak in only a couple of hours of exposure. The cosmic tagger is surrounding our detector on all 4 sides and now also on the top. So you see this is one of the walls being craned down. It's just scintillating plastic with fiber strips and then red out vesicles. And then we were finally able to raise our voltage all the way to design voltage of 100 kilovolts on July 3rd in 2024. You see us all here celebrating in the control room when that milestone was met. We have seen first events. We were lucky to get a couple of around 8 days of beam before the summer shutdown. The annual regular shutdown of the beam started on July 12th, as every year. And this is one of them. So you see it's kind of a bird's eye view from the collection plane. This is raw data, so we have not even applied noise filtering. So we see how good the noise level really is in this detector. And I see that there's particles crossing from one volume into the other. You see here neutrino interaction at the same time. And then if you zoom into that neutrino interaction, you can see it on all 3 planes here. And here we have applied the noise filtering, an initial version without any tuning. I was hoping to show you some new events because beam was scheduled to return November 1st. It didn't. It's now announced for next week. So maybe there will be new pictures first, new pictures soon. But we have quite a couple from the first 8 days. And then what we're doing is calibration measurements. So the first things, one of the first things is to calibrate the initial gain using particles, cosmics that cross the anode, cross the cathode and then stop somewhere. So you can measure the residual range, as you can see here. You need to translate basically from deposited charge to deposited energy with a couple of models and factors, some of them you're measuring in the FIT. And then you get plots like this. This is from the collection plane and then the 2 induction planes as well. The red dashed line is the muon expectation. And we clearly see that with our cosmic muons. This measurement is not so impressive in and of itself, but what's impressive is that we have done it without really tuning the entire chain. There's other calibrations that's a sensitive tool that have not yet been done, like the space charge, gain uniformity corrections, electron drift time corrections, what it actually is, and such on. And also the reconstruction in terms of finding the hits, extracting the hits, 3D reconstruction has not yet been tuned at all. And it basically just already worked, and you can do calorimetry in PID. It's really nice. The next step is to make these same plots for more highly ionizing particles such as protons, like you, for example, have seen from ProtoDUNE. So in summary, the big point I think I wanted to make in this talk is that precision neutrino oscillation experiments on both long and short baselines are key to understand some of the open questions that we have around neutrinos in the standard model. LArTPCs are quite an appealing technology to have the imaging capabilities that you need to do some of these precision measurements because they have low thresholds, they have calorimetric information, and they can separate electrons from photons. There's a lot of efforts in our community, as you've seen from the many experiments I talked about, to ramp up towards DUNE, and with SBND being the latest to come online, complementing the SBN program. we have some exciting times ahead of us looking at some data. Thank you.
Okay, Annette, we have time for some questions. Tyler?
For SBND, what sort of triggering scheme? Is it like every beam spill gets something recorded and you look later? Or is
Yeah, we have a couple of different streams. So the way we want to record the beam is we trigger on light activity. And so we're actually in the process of tuning our thresholds for that. Every 1 in 20, so we will receive the beam, when a beam spill is being sent, we receive the signal, and every 1 in 20 will actually contain an interaction for us, the others will not. So we can reduce the data stream by triggering on light activity. But then we will also have a stream that just triggers on every beam scale, but is pre-scaled to every X event or so, as a check, for example, for the trigger or for other things. And then we also take data when beam is off for our background measurements that runs concurrently. And then we have a couple of special triggers for dedicated calibration studies we want to do. For example, you can use the cosmic tagger if you want to collect cosmics from certain directions, top, sides. You can trigger on those as well.
Questions?
Yes.
Yeah, go ahead.
You sure? So, very nice talk. I have a question in the first few slides in 15 and 16, when we're talking about the, oh, is it this one? Yes, I think it's a matter effects, I believe. Sorry, I'm making you go all the way back. Yeah. I guess I'm just a little curious, given that, so what is it about the difference between the antineutrinos and the neutrinos that makes it interact differently? Is it the handedness? Or because, you know, we don't really see charge, right? But then you think about experiments thinking they might be the same thing. And so how do they all end up in the same picture? And the only thing I could think of was handedness, but I don't know.
Yeah, so when you bring a beam through matter, there is different behavior. You have very different cross sections for neutrinos and antineutrinos with matter, as well as quantum mechanic effects like that. They're different.
Okay. All right, fair. Thank you.
Right, one last question.
Oh yeah, I have kind of like two parts to it. I don't know if they're super related, but so in liquid-Argon TPCs, do you have any like specific difficulties handling pileup? And are there any like specific ways you handle that? And then also, kind of related, when you see this drift going from your two planes, you'll get this like bowing effect, right? Because there might be like issues in that drift. How do you account for that? How are there hardware corrections, or is that software based? Like, how do you do the descent reconstruction?
So the first one was first question.
Pileup.
Pileup, okay, yeah. So we don't have event rates as high that pileup really is an issue.
Sure.
But once you go to detectors with, like, let's say DUNE near detector, which is close and the beam is more intense, you will start to experience that. And so the way to handle that probably is going to be in software, trying to run reconstruction algorithms that distinguish different events. It's not as heavy as in a collider experiment is going to be, just because the interaction probability for neutrinos is so small. And then, yeah, with electrons drifting, there's a couple of effects when they drift from the cathode to the anode. There is a non-uniform field, which mostly comes from space charge building up of the ions that are produced at the same time and collecting somewhere. Basically, so all the cosmics that produce all these ions at the same time as the neutrino. But there can also be inhomogeneities by just a not perfect build of the detector. And then in addition to that, they will experience diffusion, which is different, longitudinal transfers and such. And then there's recombination, because there's a probability, especially as they drift longer, that some of the electrons recombine with argon and get captured and don't arrive all the way. So yeah, we have dedicated calibration measurements for all of these. There's models, but we will try to determine the parameters on our own. And we do that typically with cosmics. And if especially you have two handles, one is you use the CRT or the cathode of your detector, something that crosses cathode and anode, because then you know exactly where it was. It must have crossed the cathode, but if in your reconstruction it looks like it was somewhere else, you can define a pole and pull it back. And the same thing you can do with is an ultraviolet laser. which we have installed, not yet used, but you can shoot a laser beam that ionizes the argon volume, and basically a laser must be a straight track. And then when it drifts all the way to the anode and it doesn't look straight, it looks bent, you can correct it back and you can map your parameter space with that.